Hello, my name is Gerlinde Emsenhuber, and I'm going to present the paper Eye Perspective View Management for Optical See-Through Head-Mounted Displays on behalf of all authors. View management for optical see-through HMDs requires knowledge of how the scene looks to the user when viewed through the HMD. This is necessary to avoid perceptual issues such as poor legibility and decreased contrast. For example, when placing annotations in this scene, one would look for areas that are uniformly colored, dark, and untextured. Placing annotations in these areas ensures that they stand out against the background and are legible. However, the user's true view is unavailable. Because of this, previous work has often relied on the built-in HMD camera when making placement decisions. For example, consider the HoloLens 2. There are noticeable offsets between the built-in camera, the user's left eye, and the user's right eye, and as a result, relying on the HMD camera leads to incorrect assumptions about the user's true view. Returning to our initial scenario, the view that is shown here corresponds to the built-in camera view. If we make layout decisions based on this view, mid-air labels will still suffer from poor legibility and contrast when seen by the user. This happens due to the parallax between the HMD view and the user's eyes, which causes a change in backgrounds behind the labels. To avoid such issues, eye perspective rendering aims to reconstruct the user's true left and right views. The reconstructions can then be used as basis for placement decisions, which are consistent with what the user really sees, avoiding the aforementioned perceptual issues and leading to high-quality layouts. Eye perspective rendering also opens up the possibility of stereo-based optimizations, since now two views are available, instead of just a single HMD camera view. This can further improve legibility. To explore the use of eye perspective rendering in the context of view management, we developed a novel view management algorithm that starts by reconstructing the user's left and right views, and then optimizes layouts in the reconstructions. Labels move in a temporally coherent fashion, but our algorithm aims to keep them in front of a suitable background at all times. We compute the left and right reconstructions via reprojection. This method is fast and robust, and can immediately react to changes in the scene, but it does produce disocclusion artifacts, especially when the user is close to the scene. In our implementation, we avoided placing labels directly on top of disoccluded pixels. In order to find good positions for label placement, we analyzed the reconstructions with respect to 4 different criteria. Based on this analysis, we classify pixels as either good or bad label placement candidates and use vector fields to pull labels towards the good candidate pixels. We use the following criteria: uniformity, which stops labels from overlapping several regions with different colors; lightness, which excludes areas that are too bright; texturedness, which excludes areas with many small details; and finally, stereo uniformity, which makes sure that labels are placed in areas with a similar color in both eyes. The use of stereo uniformity as optimization criterion is only possible if both the left and the right views are available. We performed a study related to stereoscopic text annotations that showed that placement in stereo uniform regions does improve legibility. To evaluate the effectiveness of our eye perspective view management algorithm, we performed a within-subject study where participants wore a Project Northstar HMD with a StereoSet Mini mounted on top of it. The StereoSet Mini was used for positional tracking as well as for obtaining the RGB and depth data necessary for reconstructing the user's eye perspective. The participants' task was to rate label layouts which were optimized with different view management algorithms. The order of algorithms and layouts was balanced using an orthogonal Latin squares table. The 3 view management algorithms used in the study were a baseline algorithm, which performs no background-based optimization at all. As a result, the labels are always positioned slightly above their anchor points; an HMD camera-based algorithm, which does optimize the labels, but based on the built-in camera view. Since there is only a single view available, stereo vision uniformity cannot be evaluated, and only the other three criteria are used. And finally, our eye-perspective view management algorithm, which uses the reconstructed left and right views and applies all four criteria to optimize the labels. As for the results, participants were asked to rate the legibility of the optimized labels, as well as the severity of background issues such as blurring and double vision. The eye-perspective algorithm significantly outperformed the other two algorithms with respect to both. Participants were also asked to rate the label backgrounds with respect to our optimization criteria. This rating was performed by estimating the percentage of the label's background that fulfilled each criterion. The eye-perspective algorithm again significantly outperformed the other two algorithms. Finally, we also asked participants to rank the three algorithms in terms of preference after they had finished all evaluations for a layout. The eye-perspective algorithm was ranked first in 97% of all cases. So, to sum up our findings, we find that the use of eye-perspective rendering does improve layouts, as demonstrated by the fact that our eye-perspective view management algorithm significantly outperformed the other algorithms with respect to legibility, and was also ranked as the preferred choice in nearly all cases. Also, HMD camera-based optimization can still be beneficial. Although a single RGB camera can't be used to perform stereo-based optimizations, the HMD camera-based algorithm was still ranked as second best in 2/3 of all cases. Layouts produced by this algorithm were ranked as significantly better than the baseline with respect to uniformity and texturedness. Finally, the study showed that eye-perspective rendering can replicate the user's views with sufficient precision, even with unconstrained head movements. In our study, we allowed participants to move their heads freely, unlike previous similar studies where headrests were used. Our reconstruction was precise enough to be used as input for the optimizer, and our algorithm produced good layouts with respect to our optimization criteria. However, we also identified some areas that could be improved upon. First, regarding the occlusion artifacts and the choice of reconstruction method. We decided to use reprojection due to its low computational cost and its robustness. However, disocclusion artifacts need to be handled, especially since disoccluded areas tend to become larger when the user moves closer to the scene. This might require the use of advanced in-painting methods, or a change to different reconstruction technique altogether, such as image-based rendering. Second, regarding alternative types of optimizations. In cases where reliable scene information is not available, or if there is an insufficient number of good placement locations, the view management algorithm could fall back to alternative forms of optimizations, such as using uniformly colored billboards as label backgrounds. In cases where the scene is changing quickly, sticking the labels to real-world geometry instead of placing them mid-air can improve temporal coherence. And finally, regarding the placement optimization itself, in the study, we forced labels into locations where all criteria were fulfilled. Such a strict interpretation of the optimization criteria might lead to situations where the labels are placed at a large distance from the origin, or where no suitable layout can be found at all. To avoid this, the criteria could be integrated into a loss function for a more lenient optimization. In conclusion, we have shown that eye-perspective view management leads to improved label placements, that it can be implemented on currently available HMDs, and that it works even with unconstrained head movements. This marks the end of my presentation. Thank you.